Hello, and welcome to Module 4 of the Microsoft Certified Azure Administrator Training course. Module 4, we take a deep dive look into configuring and managing Azure virtual networks. Today's agenda focuses on the 8 sub-objectives that we need to be proficient in for passing the AZ-103 exam. Those are implementing and managing virtual networks, creating connectivity between virtual networks, configuring name resolution, creating and configuring network security groups, implementing Azure load balancers, integrating on-prem networks with Azure virtual networks, monitoring and troubleshooting virtual networks. We also provide a briefing for the lab exercises you'll come through in Lab 4. Finally, we'll close out the session with the same frequently asked questions that people ask on this training course. Let's take a look across all the sub-objectives that comprise of the configuring and managing Azure virtual networks objective of the 103 exam. Microsoft certified Azure administrators have a demonstrated and proven capability to implement most aspects of virtual networking in Azure. To pass the AZ-103 exam, there are some objectives that you need to be able to satisfy with regards to virtual networking. So let's take a look at those now quickly. We need to be able to create connectivity between virtual networks using VNet peering and VNet to VNet VPNs. We also need to be able to differentiate between virtual network gateways and gateway subnets in our virtual networks. We need to be able to implement and manage virtual networks by configuring public and private IP addresses, configuring routing to control where traffic flows between subnets and networks, configuring virtual network interfaces, and being able to break down our virtual networks into multiple subnets to structure and organize our network more efficiently. Name resolution changes a bit when we move into Azure. Yes, we may need to integrate our virtual machines with on-premises or Active Directory Domain Services DNS. However, we also need to be aware that Azure provides both a public and a private DNS hosting service. We may need to be able to configure those for our workloads, but it's essential we can work with both public and private Azure DNS for the exam. We need to be able to configure network security groups to control the ports and protocols and of traffic that can flow into and out of individual virtual network interfaces and also into and out of particular subnets. We'll also need to become proficient at creating the rules that determine what traffic can flow through a network security group and what traffic will be rejected. Azure load balancers are the cornerstone of high availability for many applications. In the platform as a service world, load balancers are created and configured for us automatically. However, when we create IaaS workloads and we want to provide network load balancing for our virtual machines, we need to be able to create and configure load balancers. There are 3 types of load balancing technologies we need to be proficient with. The first is an internal load balancer, which balances traffic from Azure virtual networks to a pool of virtual machines. We need to be proficient with external load balancers that will take external traffic into our virtual machines and balance it across that. And then also we need to be aware of Azure Traffic Manager. That will allow us to be able to route traffic from one data center or one set of public endpoints to another. Monitoring and troubleshooting virtual networks is a really important part of the exam as well. There are several tools that Azure provides to help us understand how to troubleshoot our network connectivity and our network performance. It's vitally important in the exam we're able to differentiate between the correct tool for a correct job, as each of these tools has a specific use case associated with them. Then finally, perhaps the largest area on the sub-objectives is integrating an on-premise network with an Azure virtual network. That can be done using a VPN gateway, where we can create a site-to-site VPN and a point-to-site VPN. We also need to be proficient and be able to understand how to work with express route connections. As with previous modules, there's also going to be a strong emphasis placed on verifying connectivity and troubleshooting connectivity with Azure. So again, we're going to need to be able to demonstrate that we're knowledgeable about the tools Azure provides us to do that troubleshooting with. In Lesson 8 of Objective 4, we're going to take a look at how to implement and manage virtual networks. To pass the AZ-103 exam, you can expect to run into questions that test your ability to configure private and public IP addresses, manage network routes, manage network interfaces, divide virtual networks up into virtual subnets, and to configure virtual networks. Creating a virtual network in Azure is a lot like installing a physical switch in a physical data center. What we're doing is creating an appliance that allows multiple network cards to connect with one another. Unlike a physical switch, an Azure virtual network, though, will also provide IP address management. This is a key factor of software-defined networking. So, when we create a virtual network in Azure, we also have to specify a range of IP addresses that virtual network will consist of. That allows the Azure virtual network to be able to configure virtual network adapters on each virtual machine with the correct IP address. It's vitally important that we never attempt to configure the IP address of a virtual machine inside its operating system, because that configuration should be given to it by its virtual network. We can run into serious problems if we ever have to relocate a virtual machine, or if we try and configure any kind of service bindings if we've got manually set IP addresses inside the host operating system. When we create a physical switch on-prem, it's entirely likely that we might want to divide up that switch into multiple virtual networks. What we're doing within Azure with subnets is dividing a virtual network up into subnets, very similar to why we might divide a physical switch into VNets. The idea being is we might want to isolate part of that network to apply different firewall rules, to zone out and separate connectivity between devices. So, when we create an Azure virtual network, we have to configure an IP address range for the entire virtual network. That determines what we call the subnet gateway. That's the net bit of the Azure virtual network that allows individual subnets to communicate with one another. When we create a virtual network, a gateway subnet is created for us automatically. We're also prompted, and it's mandatory, that we create at least one subnet in that virtual network. So what we need to do when we create a subnet is we take a subset of the IP addresses from the entire range and create a smaller subsection of that network that we can add virtual machines to. Now, it's not possible to add a virtual network card directly to the gateway subnet or to the entire virtual network. All virtual network cards have to be attached to a subnet, so it's vital that we have at least one subnet in our Azure network. When we create one or more subnets in an Azure VNet, by default, it's configured for open routing. That means a client in subnet A can communicate with a client in subnet B without anything interrupting it. That flow of traffic is open by default. Also as well, the gateway subnet will act as a router to allow us to connect to other Azure VNets as well if we allow it to do so. As you can see, what we've done here is we've created an IP address range based on the TCP/IP4 range of 10.0.x.x/16. The 16 CEDA value means that we're using a 255.255.0.0 subnet mask, meaning 10.0 is the network number and the individual 0.x would be host numbers in that subnet. What we're doing at the subnet level, though, is I'm dividing that class B range of addresses into two class C subnets. So we have here two networks with the network number 10.0.1.x/24, meaning it's got a class C subnet mask of 255.255.255.0, and a subnet B which has an address range of 10.0.2.x with the last digit being used to identify a host within that subnet. So I then have two subnets that contain up to 256 hosts in each. The idea being then I've got capacity then to add additional subnets later on, and I can add additional virtual machines into each subnet as well as I see fit. When I create subnets in Azure, by default, the configuration is for open routing. That means that by default, any virtual machines in subnet A can openly communicate with subnets in virtual B without the gateway network modifying that traffic. Open communications. However, if I want to force traffic to obey certain rules, so let's suppose if I want any traffic going from subnet A to go through a firewall or a web proxy, I can implement a routing table rule in the gateway that will force that traffic to go through a particular route in order to get to its destination. Not only can I use that for optimizing connectivity, I can also use it for forcing security scenarios, like forcing outbound web traffic to go through a web proxy. Every virtual machine has to have at least one virtual network adapter. My virtual network adapter can have multiple IP addresses bound to it. That means even though I have one network card, it believes it's registered against two IP addresses. Now what I can do here in Azure is I have to have a private IP address that connects my virtual network card and therefore my virtual machine to my Azure virtual network. What I can also do as well is configure each virtual network card to have a public IP address. That's connected through Microsoft's Edge network to the public internet. If I want to allow inbound internet access from clients on the public internet onto my virtual machine, I can do that by using a public IP address. So, public IP addresses and private IP addresses. Private IP addresses, if I'm connecting with a virtual machine on my VNet, I use the private IP address. If my virtual machine wants to connect out to a website or a web service like update.microsoft.com, or it wants to connect to time.microsoft.com, that outbound internet traffic will also go through the private IP address, and it will communicate out through my gateway out to outbound internet access through my Azure virtual network. If I don't have a public IP address on my machine, I can still by default connect to the public internet. Public IP addresses are only there for inbound internet access. That means if I say host a website on my virtual machine or a service or a file share, and I want people to externally be able to come in and connect to that over the public internet, that's the traffic that will use the public IP address. One of the great misconceptions of public cloud computing is that many security analysts didn't realize there was a difference between private IP addresses and public IP addresses. The assumption used to be made with public cloud that every IP address you had in a network was public and that every IP address was publicly available. And that's just not true. There's a huge difference in privacy between a private and a public IP address. When we create a virtual network card, by default, it will only create a private IP address for it. It's only if we specifically tell it that we want to configure a public IP address for us. Both private and public IP addresses can be dynamic or static. The number of private IP addresses we have is determined by the number of IP addresses in the virtual networks and subnets we've configured. The total number of public IP addresses, static public IP addresses we can have, is determined by a limit that's imposed on our subscription. By default, there is a limit of 1,000 public IP addresses attached to every Azure subscription. But if you want to create 1,001, you can ask Microsoft to raise that limit and they'll consider doing that for you. It's good practice to use static public IP addresses sparingly, which means only use them when you should. But these things are in no great short supply. So it's quite possible to have a public IP address for each website or for each virtual network that you expose out to the public world. I can also attach multiple virtual network cards to my Azure virtual machines. Now you have to be aware that there is a limit to the number of virtual networks each virtual machine can accommodate based on its size as a VM. The larger VMs can accommodate up to 8 or 16 virtual network interfaces. Smaller ones may only be able to accommodate 2. It's all down to the size and specification of the virtual machine that you buy though. So what I can do is I can have 2 virtual network cards in my machine and I can use them to connect to 2 different Azure VNets. I can also have public and private IP addresses on both virtual network interfaces. Again, just with a single virtual network interface, all my VNet configuration will be applied to it through software-defined networking, which is facilitated by IP address management on the Azure virtual network. If I want to configure a virtual network with a static IP address, I can do that through the virtual network interface's resource object in the Azure portal. Let's take a scenario where I've created a SaaS application. Maybe it's a cloud service or it's a SQL Server PaaS database instance, or it's a storage account. Now, because I've created those PaaS offerings or PaaS resources in Azure, they will, by their very definition, have a public endpoint, which means they can be accessed through the public internet. Now, on each of these resource types, we have ways of restricting what traffic can connect. So, for example, a service endpoint, we can configure a load balancer to restrict what clients can connect to it. We can implement a firewall on an Azure service and on an Azure SQL connection to restrict what machines can connect and query the database. Storage accounts also have the ability to apply a firewall to them as well to restrict connections from the inbound internet. But what if we want our virtual machines on an Azure virtual network to be able to communicate directly with those PaaS offerings without having to traverse the public internet? The way to do that is by enabling service endpoints, and that's a two-step process. First of all, I need to configure my Azure VNet to support service endpoints, and I have to whitelist the type of offerings that are allowed to connect directly from that VNet. The second step is to go on to the actual PaaS offering itself and configure the PaaS offering to actually have a service endpoint and to marry up that service endpoint with the virtual network I want to allow connectivity to. It's also possible through the same dialog box on the service endpoint to block connections to the storage account, database, or PaaS application from the public internet, forcing it to be private only. It's important to note that connections from a virtual machine to a service endpoint don't just happen over the virtual network. What we're not doing here is taking the service endpoint and attaching it to our virtual network. What we're doing here is creating a route that allows my virtual machines to be able to connect to a private IP address that exists in a different subnet, that exists in the Microsoft Edge network, to connect to that database or storage account or web application. That's not the same thing as joining the database to the virtual network itself. What that means it will look like is these virtual machines down here will have an IP address from that virtual network, but these services over here, their service endpoints, won't have an IP address that comes from that virtual network. They'll have an IP address that comes from Microsoft's Edge network. All we've defined is a route from this virtual network to each of those endpoints. In Lesson B of Objective 4, we're going to take a look at creating connectivity between virtual networks in Azure. In the 103 exam, you're going to come up against questions that test your ability to create and configure VNet peering, VNet to VNet VPNs, and also to verify connectivity and to create a virtual network gateway. Not only will you come across theory questions, I can pretty much guarantee you're likely to run into exam simulation questions where you'll be asked to perform the configuration steps in a simulated version of the Azure console. I'd like to take this opportunity to provide a bit of disambiguation. There are three types of gateway resources we'll talk about when it comes to virtual networks. The first one is a gateway subnet. Think of the gateway subnet as being the interconnect between multiple subnets in the same virtual network. Remember, you can't attach a virtual network card directly to a gateway subnet. You can only attach it to an actual subnet network. Then we have the VPN gateway. Try and think of the VPN gateway as being like the virtual appliance that allows us to connect that virtual network to another network. It's a bit like saying, this is the router that we'll use to connect to the on-prem network or to connect to the site-to-site network. Or it's the router that will connect to the VPN clients on the public internet. And finally, we have another type of gateway, which is the express route gateway. That is specifically designed to terminate express route circuits onto our Azure virtual network. So when we create an Azure virtual network, it will automatically create a gateway subnet for us. It will also mandate that we create at least one subnet on that network as well. Afterwards, we can then choose to create a VPN gateway, but we can only have one VPN gateway at a time. We can have a VPN gateway, and we can also have a maximum of one express route gateway as well. The idea between allowing a VPN gateway and an express route gateway is to allow us to be able to connect to provide a level of resilience in our connection back to on-prem so that we can use ExpressRoute as the main mechanism, but then fall back to the VPN connection if there's an issue. Or maybe we've got some offices that can only connect through a VPN gateway and some that can only connect through ExpressRoute. So we're allowed to have both types of connections coming into the VPN. But remember, only one VPN gateway, only one ExpressRoute gateway, no multiples of either. If I have two virtual networks in Azure, the intention is that they will be separate networks when I create them. But if I want to join the two together, I need to create one of two artifacts. If both my VNets exist inside the same Azure tenant, I can create an Azure VNet peering. What that will do is it'll basically create a forwarding route between virtual network A and virtual network B, meaning I can route traffic between the two quite happily. VNet peering allows VNets to communicate with each other over Azure's private physical networks. It's essentially a network extension, if you like. Because that connection is private, there's no network level encryption applied on that peering. But what it does mean is that machines in VNet 1 can communicate with machines in VNet 2. As a prerequisite to creating the VNet peering, we have to check, and the Azure portal will validate to make sure that VNet 1 doesn't contain any IP addresses that overlap with VNet 2. If that is the case, you won't be able to create a VNet peering between the two of them. And the only way to resolve that will be to re-engineer the virtual networks and move resources from one to the other so that you don't have overlapping IP networks. It's important to plan your virtual network IP address ranges from the outset to prevent against overlaps. If I want to provide connectivity between two VNets that either exist in different Azure subscriptions, or maybe we have a VNet that exists in Azure and one in AWS, I can use the VNet to VNet peering option. What that means is, when I create my VNet gateway for the Azure VNet, I could basically create a VNet to VNet connection that will provide an IPsec tunnel between both of those networks. Now that traffic will actually flow through Azure's edge network. So the assumption is it's using a public connection. Therefore it uses IPsec to encrypt that tunnel, and it uses Internet Key Exchange to authenticate the connection when it creates the tunnel. Once that's in place, my Azure VMs can communicate with one another. However, it's important to bear in mind if I'm using a VNet to VNet VPN that spans multiple Azure regions, I will have to pay for the traffic egress as it goes from one region to another, whereas within one region, it will be free. There are a lot of companies who consume large amounts of Azure that are just very small companies with a very finite number of employees. It's entirely possible that we may have a number of developers and infrastructure management resources who need to have access to our Azure VNet, but maybe they don't work from an office. Maybe they're either home-based or there isn't a site to connect in. Maybe all the resources live in Azure. So to support those kind of scenarios, we offer a second type of VPN tunnel. That's a point-to-site VPN. With a point-to-site VPN, what we do is we create a VPN gateway just as we would with site-to-site. Then when we create that, we'd specify to use the point-to-site VPN style. We need to create a public and a private key using the makecert utility or by using a public key digital certificate provider. Then we take that key, we issue the public key to each machine that's going to have a connection to the VPN. And we also give it a phone book entry in the VPN connections section of Windows networking. What that basically means is the end user on a virtual machine can connect into an Azure VPN. They have to initiate and terminate the connection manually when they connect in. When they join in, they'll be given a virtual IP address inside that virtual network that allows them to communicate with the resources inside the VPN. But this is a great way of providing connectivity without necessarily having to have resources come to an on-prem network, connect into our private virtual networks in Azure. So there are two types of tunnel provided by Azure point-to-site VPNs. The first one is using site-to-site tunneling protocol, and the second one is using Internet Key Exchange. Finally, for the exam, we need to be aware of site-to-site VPN connections. We'll cover off site-to-site VPNs in much greater depth in lesson H of this module. So, what we're doing with a site-to-site VPN is we've got one or more Azure virtual networks. We create a VPN gateway on that virtual network. Then what we do is we pair up that virtual network gateway with an on-premises router that creates and manages and maintains an IPsec tunnel between the on-premises location and the Azure VPN gateway. What that means is on-premises computers can communicate with resources based in the Azure virtual network. Site-to-site VPNs provide connectivity between an on-premises network and an Azure VNet. The next type of network-to-network connectivity we have is an express route circuit. Here what we do is we work with an organization called a network service provider. What they do is they provide a network circuit between your physical premises and Microsoft's edge network. When you buy an express route circuit, they provide a resilient connection, so there are two circuits that connect you in the event that one's lost. These circuits also support bursting, so you can increase and decrease the amount of bandwidth that you consume on demand. Essentially, with an express route circuit, what we're doing is providing three peerings. We have the Microsoft peering that allows computers inside our private network to communicate with Office 365, Dynamics 365, Azure AD, or any of Microsoft's software as a service offerings over a private connection. They still connect to public software as a service offerings, but the express route circuit terminates inside the Microsoft Edge network inside the Azure region, the regional data center. That means at no point in time is any of the traffic going from your computer to the SaaS offering is going out over the public internet. We also have the public peering. So when we create an Azure offerings that have a public endpoint to them, so a storage account, a PaaS database, a virtual machine with a public IP or an availability or scale set, we can have a connection directly from our on-prem network to the public IP address of those machines. And again, that can be committed over the express route circuit, which is terminated in the edge network, meaning we're connecting to the public IP address of those resources, but our connection goes through a private circuit and ends inside of Microsoft's edge network. So again, at no point in time is any of that traffic disclosed to the public internet. Then finally, we have the private peering, and that's where we join up our on-premises network through a private circuit to one or more Azure virtual networks in Azure. Express route circuits provide a private and resilient connection between on-premises networks and Azure VNets. There are three styles of site-to-site connectivity that we can achieve. If we're happy for our traffic to be sent over the public internet and encrypted using IPsec, it's fine to use just a site-to-site VPN to achieve that. We don't need an express route circuit to connect to Azure unless we need to have a private circuit that connects us to Azure. The first Azure provider scenario is called the exchange provider. Here, our express route circuit provider provides a dedicated connection from our physical premises or data center into their partner location, which is usually like an exchange type location. Then from that exchange connection, they have a dedicated circuit that they share us with into the Windows Azure Edge network. In the third scenario, the network service provider scenario, what we do is our network service provider hosts an MPLS cloud for us. And what they do is they add a leg off that MPLS cloud for our wide area network into Azure. Now with both the exchange provider and the NSP models, they have a separate breakout for public internet access. So any traffic going out to the public internet is not handled by the express route circuit. That's really important to bear in mind, because with express route circuits, you're paying for ingress and egress, you're paying for the amount of bandwidth that you consume. So you want to make sure that you don't unnecessarily use those circuits to access stuff that could just be accessed publicly. So in summary, an express route circuit can also provide an MPLS WAN extension into Azure. So we're extending our network into Azure rather than just an individual site. In Lesson C of Objective 4, we're going to learn how to exploit Azure Public and Azure Private DNS name resolution. AZ-103 is going to throw some questions at us about Azure DNS and how we use it to configure name resolution. We need to be able to configure Azure DNS, to be able to configure custom DNS settings, and to be able to configure both private and public DNS zones in Azure DNS. Azure DNS is a platform as a service DNS offering. That means we don't need to be bothered with any infrastructure to host our records. There's a lot of benefits to using Azure DNS for our name resolution. The first one being that if we're using one set of tools to deploy our code and the same set of tools to deploy our virtual infrastructure, wouldn't it be great to have the same set of tools to be used to configure our public DNS records? Azure DNS uses a global network of name servers that respond to DNS queries. They use a technology called Anycast networking. What that means is if I do a DNS query, I'll automatically be routed to the closest name server to me on the internet. That means I get the best possible response for name resolution. I can also rely on Microsoft Global Network of DNS servers because they're highly available. I don't have to get caught up in configuring individual DNS servers and load balancing them or providing multiple master replication around the world. Azure DNS, unlike other DNS providers, allows us to update a record with a new IP address in a matter of seconds. We don't have to wait, say, 24 hours for a record to be created and populated out around the world. Azure DNS now also adds the ability to provide a private zone, which is where we can provide name resolution for our private networks and VNets using a software as a service model. Put simply, Azure DNS provides public and private hosting zones. Public zones are DNS records that are available for people on the public internet to resolve and receive an IP address from. Private DNS records are usually for internal addresses that we don't necessarily want external people to be able to identify. So, generally speaking, public DNS records are for services. Private DNS records are for individual machines and services as well. It's vital to remember that Active Directory domain services will still require us to implement the DNS service on each domain server or each domain controller server for it to be able to function correctly. Something else to point out as well, that Azure DNS doesn't support the DNSSEC protocol. However, in most cases, we can negate the need for DNSSEC by consistently using HTTPS and TLS encryption in our applications. If DNSSEC is critical to our requirements, maybe we've got a regulator that's saying that we have to use DNSSEC for our hosting records, there's no reason why we can't use a third-party hosting provider to provide us with a DNSSEC service and integrate that with Azure DNS. It's very common that we'll leverage Azure DNS and Azure Traffic Manager together to provide us with a form of failover and global traffic management. What we can do here is use a global traffic manager to manipulate the DNS records hosted in Azure DNS. So we can update the IP address to reroute traffic from one Azure region to another region, or from one endpoint of our application to another. What that means is Azure Traffic Manager can monitor the health of our application infrastructure in one data center. If it becomes unhealthy, forward our traffic to another one. There are several other profiles that Azure Traffic Manager and Azure DNS can support, and those include things like service location. So we can ensure that the user gets sent to the endpoint that's closest to them in the network. We can also use it as well to provide preferring to send traffic to a given resource and using the other endpoint as overflow. When we get into the labs, we're going to configure each of those scenarios. In Lesson D of Objective 4, we're going to learn how to create and configure network security groups, allowing us to control the traffic that can flow onto a virtual network card or into an entire virtual subnet. As a Microsoft Certified Azure Systems Administrator, you need to be able to use network security groups to control the traffic on your networks. Now we can use that to create network security groups. We need to be able to associate network security groups with a subnet or an individual network interface. We need to be able to identify what ports are required for an application to communicate effectively, and to also evaluate all the security rules that apply to a particular bit of traffic when multiple network security groups are applied. Network security groups allow us to filter and restrict what traffic can flow onto a virtual network interface or into a network subnet. It does that by using a series of rules. Just like with the traditional firewall, what we're able to do is implement a rule that either allows or denies particular types of traffic to come into a network interface or into a subnet. We can configure the source, so we can whitelist particular sources that can communicate and block others, or we can block specific ones. We can also control by destination. We can also control based on the service or protocol that's allowed to flow through the network security group. When we attach a network security group to a network interface, what we're doing is restricting the traffic that can be sent from a virtual network to an individual virtual machine. So let's suppose we have a virtual machine that only hosts a website and it will only ever dish out queries, it will only ever respond to queries on port 80. It would be good practice there to implement a network security group that blocks any traffic not flowing over port 80 from going onto that network card. So we'd use a network security group to do that. It's also possible to apply the same network security group to multiple virtual machines. That way we can have one set of configuration consistently applied to multiple network adapters across multiple virtual machines. That's really good for configuring consistency. In summary, we use network security groups attached to virtual network cards to restrict the traffic that can flow into or out of an individual VM. I can also create a network security group and attach it to an entire subnet. What that means is the network security group rules apply to any traffic that comes into my virtual network or into my virtual subnet. That way I can restrict the traffic that actually comes onto the virtual network in the first place. I can apply that not only at a virtual subnet layer, I can also apply network security groups to perimeter type devices like Azure firewalls and also Azure network load balancers. That can become really helpful to us. In Azure, we'll typically be paying for ingress and egress traffic, which is the amount of traffic coming into our network. If I use a network security group to block ports and traffic that's not relevant to my platform, that's a really effective way of cutting down the ingress into my environment. Although that traffic actually makes it into the Azure environment, it's dropped at the outside by the load balancer, so it doesn't come onto my private network. Therefore, it's not regarded as ingress traffic. Here in this example, I have 3 tiers for my application. I have a web tier application at the front end. So perhaps in there, I'll only allow traffic to communicate over port 80, 8080, and 443. Then in the business tier of my application, maybe I'll only allow traffic to communicate over port 443 between the web tier and the business tier. I can use the network security group to drop ports that aren't using that type of traffic and also to ignore traffic that doesn't generate from one of the 3 VMs in that other subnet. Finally, I have a data tier where presumably I'm probably using some kind of database like a SQL server. So here I might apply a network security group that blocks traffic coming in unless it's coming in from the business tier and it's using port 1433 to connect to the SQL instances. In summary, we use network security groups on subnets to restrict the traffic that can flow into and out of a subnet. If I was to follow the good practice of applying defense in depth, I would apply network security groups both to my virtual network interfaces and to my subnets. That way, not only am I restricting what each individual network interface can consume, but also what traffic can flow on the virtual network as well. So, unfortunately, whilst that does give us a more secure environment and makes it harder for attackers to compromise us, it also makes troubleshooting a little bit more complicated because we've got multiple network security groups along the route that traffic might take from one virtual machine to another. So, built into the configuration of a network security group, we have a tool called Effective Security Rules. What that allows us to do is pick a virtual machine and a virtual network interface for it and identify which network security groups are associated with it. That helps us build out the overall list of effective rules that are in place, allowing traffic to come to it and go from it based on its destination and source. It's a really powerful troubleshooting tool to use if we're trying to figure out why traffic won't flow as we expect from one network, from one machine to another. In Lesson E of Objective 4, we're going to learn how to implement Azure Network Load Balancers. In the Azure Administrator exam, you're going to run across questions that test your knowledge of internal and external load balancers. You'll also be expected to be able to understand how load balancing rules are applied and configured. Being able to troubleshoot load balancing is something that frequently comes up in the AZ-103 questions. An internal network load balancer takes traffic from an existing internal Azure virtual machine or virtual network and balances it out to one or more virtual machines in a back-end pool. The idea being, by providing a pool of multiple virtual machines running the same stateless application, we're able to provide a level of fault tolerance. If the first virtual machine in the back-end pool were to fail, the load balancer's health probes would detect that the virtual machine is no longer available. It can then redirect any inbound network traffic to one of the alternative virtual machines. We also have performance probes as well, which can look at the amount of traffic coming through or the performance of the virtual machine and try and distribute the load out across a pool of virtual machines. It's also possible to apply a network security group to an internal load balancer. That way, any traffic that won't be serviced by the back-end applications can just be dropped before it hits the internal load balancer. In summary, internal network load balancers balance traffic from private IP addresses to a pool of Azure virtual machines. This allows us to facilitate scenarios like scaling, auto-scaling, and fault tolerance. External load balancers function very similarly to internal load balancers, with one key difference. The connections that work with the network load balancer come from the external internet. That means external network load balancers have a public IP address associated with them. So we can publish out a connection using a load balancer to the public internet to allow somebody to, say, browse to a website or access an application running on a pool of virtual machines in the back end. In summary, external network load balancers balance traffic from internet clients to a pool of Azure virtual machines running on an internal virtual network. Both internal and external network load balancers allow us to implement a combination of rules on there. When we consider a source rules examine the packets as they come from the client computer that wishes to connect to the workload. Destination rules apply to traffic as it's being sent from the load balancer to the machine in the virtual machine pool at the back end. The types of rules we can create on the load balancer include source IP. So what we can do is whitelist or blacklist particular IP addresses or ranges of machines from being able to communicate with the load balancer. So maybe we only want to allow certain IP addresses to connect, or maybe we want to block particular IP addresses that have been used in attacks from being able to connect. We can create source port rules. So for example, if I can use my network load balancer to take connections that come in over port 80 and maybe translate them into using port 8080 connections to connect back to the back-end pool. I can use destination IP address and destination port rules as well to determine when traffic comes in for a particular service or over a particular port or to a particular IP address, which back-end pool or which individual server in a back-end pool that traffic gets sent to. I can also implement protocol level rules. When we get into the labs, we're going to get you to configure a couple of external network load balancers and to implement a combination of the different rules so you can see how these work in practice. The third load balancing solution that Azure provides us is Azure Traffic Manager. Unlike internal and external load balancers, which balance traffic between pools of virtual machines, Azure Traffic Manager is used to balance traffic between external load balancers, ideally balancing traffic between one Azure region and another, or one implementation of our infrastructure and another. Azure Traffic Manager works not by shaping traffic itself, but by modifying DNS records. So when a client queries a DNS record for a web service, say it's contoso.com, the IP address it will be given to connect to the service will be dictated by the traffic manager. That means Azure Traffic Manager can look at that DHCP request and say, okay, because you come from this IP address and that IP address is known to be in the eastern area of United States, we'll balance your traffic and send your request across to the East US region and put it onto the load balancer there, which will send it to a virtual machine. The idea there being is we're directing your traffic to the closest infrastructure to you that's likely to give you the best possible performance. We can also use Azure Traffic Manager with probes, so that Azure Traffic Manager will constantly be looking at the health and availability of our public load balancers to see if one of our regions has gone offline. That way, if our application fails in Eastern US, I can then tell it to forward all traffic to the central US region so we can still access the service, even if we've lost an entire region. Network load balancing is an essential and mission-critical component of our applications. The whole point about implementing network load balancing is to avoid a single point of hardware failure in our back end. Azure Network Load Balancing does this by balancing traffic to either multiple regions or to multiple virtual machines in a pool. So it's important to bear in mind that the network load balancer itself is not a single point of failure. Although we logically create one network load balancer appliance or resource in Azure, that resource is actually based on fault-tolerant hardware that's supported by multiple physical instances underneath the waterline. We don't need to worry about that configuration. We just need to appreciate that that network load balancer itself is highly available. It's really important that we check out the health of our network load balancers, and we can do that using the Service Health tool. If you've read through the previous modules, you know that Service Health is typically geared towards the health of resources underneath Azure, whereas Azure Monitor monitors the resources we've created ourselves. So in Azure Health Monitor, what we can do is we can add a diagnostic probe for each of our external load balancers, and there we're able to see the health and availability of our external load balancers. We also get to see the health history of those external load balancers and any planned maintenance or service issues or health advisories from Microsoft that might affect the availability of those external load balancers going forward. In Lesson F of Objective 4, we're going to learn how to monitor and troubleshoot virtual networking with the tools that Azure provides for us. As a Microsoft Certified Azure Administrator, one of the more common types of activities you'll get involved with is monitoring and troubleshooting virtual networks. The exam will test in depth your knowledge and proficiency at being able to monitor an on-premises connectivity to an on-premise network, use network resource monitoring, use the Network Resource tool, Network Watcher resource tool, troubleshoot external networking, and also troubleshoot virtual network connectivity inside of Azure. One of the massive benefits of software-defined networking in Azure is the fact that all the management tools are built in for us through the Azure portal. Here we can see we're using the Azure Network Performance Monitor tool to monitor the performance of connectivity from multiple external sources into our Azure service endpoint. We can do this by deploying a diagnostic agent onto external machines and configuring it with a diagnostic test to target the service endpoint. So for example, here we've got a test that's being deployed to multiple external computers that's targeting an IP address and targeting a DNS name on a particular port and protocol, and it will test the optimal route to connect to that resource for us and let us know if particular routes fall down and make a slower connection. We can use this to assess the performance of our services from more than one location and take into account the network performance aspects rather than just what's hosted in our data center. Because what we're monitoring is just service endpoints, which effectively just require us to know the URL of the resource, we can also use Network Performance Monitor to look at the quality of a connection for Azure virtual network connections, public endpoint connections, and also software as a service offerings. So you can use this as a way of setting up performance monitoring for Office 365 resources and Dynamics 365 organizations too. Put short, Azure Network Performance Monitor, we can use that to monitor service connectivity from multiple vantage points to form a central 360-degree view of how available our services are. Network Resource Monitor allows us to create diagnostic tests and attach them to various resources in our network. That way what we can do is test connections to different URLs to see how well the connections are performing and if a connection fails. Ultimately, what's being transmitted is a set of HTTP responses. So we're able to build out very simplistic type diagnostic tests to check and see if an application is responding as it should do in a timely manner. Azure Network Watcher provides us with a graphical representation tool that builds out a topology of connectivity between our components. So for example, here in this view on the left-hand side, we're able to see the relationship between an Azure VNet, its component subnets, network security groups at the VNet and the network card instance, and individual servers and virtual networks. We can also see in there as well a network load balancer as well. This is a great way of building up a graphical view of our network so we can understand where the relationship between components, to understand where failures may be occurring. That's our topology of view. One of the things we do need to do though is to enable Network Watcher on our networks. It's not enabled by default, and generally speaking, we only enable it when we need to do troubleshooting. Network Watcher gives us four diagnostic tools. The first one is IP flow verification, next hop analysis, security group views to help us identify the filtering that may be in place, and also packet capture to allow us to capture the actual packets of data flowing from one network interface to another. We also have some performance monitoring on there that will have us have a look at our network subscription limits, and there are also logs in place as well to monitor the decisions network security groups are making when evaluating which packets of traffic to pass or to deny. And we also have diagnostic logs as well that tell us about any events and errors coming from the virtual network. Put short, Azure Network Watcher allows us to monitor, diagnose, and gain insights into our network infrastructure between various points. Network Performance Monitor allows us to graphically visualize the performance and health of our virtual networks. In this dashboard here, what we can see is summary information about the performance of our ExpressRoute circuit. We can see we have one circuit that's in a healthy configuration. We've also here got monitoring of our service endpoints. So we can hear here that we've got two tests that are running. One showing an unhealthy result and the other one showing a healthy one. Then we can also have performance monitor as well that will have a look at our subnet links and our network links for us and tell us which are in a healthy state and which are in an unhealthy state. This is an ideal dashboard to put in front of your network team, and also to configure some alert notifications behind this as well, so people can come in here and respond to issues with the network. Azure gives us two tools for troubleshooting external VNet connectivity. The first one is VPN diagnostics. We use the VPN diagnostics tool inside Network Monitor to have a look at the configuration of our VNet and to send some diagnostic traffic across there to see what results are generated. We basically configure which VPN gateway we want to test the connection over, and we start troubleshooting. That way it'll send some telemetry across, it'll send some diagnostic data across the connections to see what's happening. We also have a similar tool for use with ExpressRoute circuits. The difference between ExpressRoute and a site-to-site VPN, however, is that ExpressRoute circuits are managed by your circuit provider. So what that means is the monitoring, we can just turn that on and see if it's working. And if it's in an unhealthy state, most of the time we just log a support ticket and give that to the network service provider to have them resolve it. It's only if there are any configuration issues on our ExpressRoute VPN gateway that we need to take any action. Most of the time here, it's for the network service provider to provide the right level of support and coverage for us. Microsoft recommends an approach for us to use when we're troubleshooting internal VNet connectivity. The first step is to identify whether our virtual network interface is configured correctly. Then we take a look and see whether network traffic is being blocked by any network security groups or user-defined routing rules. Is any network traffic being blocked by a VM level firewall, like the Windows client firewall that runs inside the operating system, that could be getting in the way? Are any VM apps or services that are running on the VMs, have they been configured to listen to the correct port, say in IIS's port bindings? We should check whether the problem is being caused by network address translation or secure network address translation. Some applications don't play nice. Some ports and protocols don't play nice with network address translation. We need to check whether traffic is being blocked by any of the features of classic networking components. And if it is, ideally what we would do is migrate the virtual machines and migrate the network up to being, instead of classic resources, being Azure Resource Manager resources. It's entirely possible we need to reach inside our virtual machines and use some of our traditional skills, like using TCP/IP tools like ping, traceroute, ipconfig, NShosts, to look at the configuration of traffic, to look at how the operating system is experiencing connectivity from one component to another as well. So it's important to remember we've got the ability to look at the fabric through the Azure portal and things like NSG flow logs and IP flow verify in Network Watcher, but we also have an existing tool set of IP configuration tools inside the operating system that we may need to leverage as well. In Lesson G of Objective 4, we're going to learn how to integrate our on-premises network with an Azure Virtual Network. Perhaps the biggest and most significant sub-objective of the AZ-103 exam is integrating an on-prem network with an Azure Virtual Network. We're going to take a look at how we implement a site-to-site VPN and connect an on-premises network into Azure. We'll also take a look at how ExpressRoute provides a private circuit connection for that. If we want to connect an on-premises office to Azure over the public internet, we configure a site-to-site VPN. The architecture of a site-to-site VPN comprises of a couple of components. The first one is the router appliance deployed on the on-premises site. Ideally, that would be one of the supported ones that Microsoft supports. We can see that in the list of supported router devices. We use that router to establish an IPsec tunnel over the public internet into our Azure VNet gateway. The authentication around that IPsec tunnel is performed using Internet Key Exchange. So when we create our Azure VNet gateway, we'll also create an IKE key that needs to be configured on the router to give it the ability to authenticate. Within Azure, we take our existing Azure VNet and we add a virtual network gateway to it. Essentially, that's like adding a router to the network that allows it to make communications with VPNs. Once we create our Azure VNet VPN, it then provides us with the ability to create connectivity to from a virtual network to our on-premises environment. In addition to creating the virtual network gateway, we also need to create the Azure local network gateway. Roughly speaking, all the local network gateway is a set of records that identify to Azure which IP ranges we have in our on-premise network. That helps the VNet gateway identify which packets of traffic need to be routed across the site-to-site VPN to reach their destination on premises, and which ones don't. Before we can configure a site-to-site VPN, we first of all need to have configured our virtual network. Once that's done, we then go into the marketplace and add a networking appliance. Specifically, we need to add the virtual network gateway appliance. Once we add that, we obviously need to give it a name. We need to choose which type of gateway it is. There are different types of gateway models to support a VPN connection and for an ExpressRoute connection. If we're going to connect over the public internet, we choose a VPN gateway type. There are two models of VPN we can create. One is a route-based one, the other one is a policy-based one. Policy-based ones allow us to provide a lot more granularity in what we configure, and it can support scenarios like providing multiple virtual network gateways and multiple routers on-prem to provide resilience in the connection. Azure makes virtual network gateways available in different SKUs, so there are a range of sizes available that determine how many Azure virtual networks the gateway can connect to, but it also determines the overall bandwidth of influx of inbound and outbound data that can be accommodated. When we create the virtual network gateway, we need to attach it to an Azure virtual network, and we also need to create a public IP address for it. Because it's going to initiate a connection over the public internet, it needs a public IP address to communicate and establish a tunnel with the on-prem router. Obviously, just like everything else in Azure, we need to specify which subscription will be used to pay for this resource. Now, there is a cost for a virtual network gateway in our environment, so it's important that we identify the right subscription to pay for that. And as always, we need to choose the correct location to deploy our virtual network gateway in. The rule of thumb is you deploy the virtual network gateway in the same physical location as our virtual network. Now that we have our VPN gateway configured, the next step is to configure the local network gateway. Again, we do that by going into the marketplace, choose networking offerings, and by deploying a local network gateway appliance. A local network gateway is not a complex concept by any shape or form. Essentially, a local network gateway is a list of IP addresses and ranges that exist in our on-prem network. We configure that in Azure so that Azure can configure our VPN gateway with a routing table that tells it which bits of the network are on-prem and which bits are in Azure. That way, Azure can configure the VPN gateway to optimally route the traffic over the VPN, so only the traffic that needs to go over the VPN does so. When we're configuring a local network gateway in the Azure portal, what we need to do is give it a name, we need to specify an IP address for it. We also need to add in the IP address spaces of our on-premises networks. And like all of the things, we need to create a subscription, so we need to configure which subscription pays for the local network gateway, which resource group it exists in, and also which physical location it resides in. Just like the VPN gateway, our local network gateway should reside in the same physical location as our virtual network. Finally, once we've created our virtual network, our VPN gateway, and our local network gateway, the next job is to join the two things together. What we would then do is then go into the properties of our VPN gateway, move to the settings section and click on connections. From there, we can define the connection that exists between our local network gateway and our virtual network gateway. As you can see from this slide, the settings that we need a name for the actual connection. We need to determine whether it's a site-to-site connection using IPsec or whether it's a point-to-site connection from client to client. And that will determine when we configure the initiating virtual network gateway and the receiving local virtual network gateway. We also use this interface to create a shared key. That shared key gets input onto the VPN appliance or the router appliance on-prem to allow it to authenticate with this connection. And again, we also need to choose resource groups and locations for the VPN gateway. It's really important that we choose the same resource group and the same location to host our VPN gateway that we chose to host our virtual network in, because those resources need to reside together. If we try to create these resources in the wrong location, we're not going to be able to see the virtual network to attach it to. There are some circumstances in which we can't allow any of our data, regardless of it being encrypted or not, to flow over the public internet. Examples might be where we're using healthcare information, or maybe we're using defense level information. So, an Azure Express route gives us a connection from our on-premises network into Microsoft's Edge network using a service provider's network. The network service provider will use layer 2 encapsulation to make sure that traffic flows only across their circuits into Azure. It uses a private connection, so at no point in time is our information going out over the public internet. We're using the circuits provided by our network provider. The way an express route circuit works is it provides 3 peerings. The first peering is what we call the private peering. That allows us to connect our edge network directly to our virtual networks in Azure. That way, the things we have running on Azure virtual networks will act as if they were just in a private data center. We have a public IP address peering as well. That means our on-premises workloads can communicate with PaaS type offerings or anything with a public endpoint hosted in Azure. However, we won't connect them over the public internet. We'll make a connection through ExpressRoute into Microsoft's Edge network, and from there we'll connect to the endpoints of those PaaS offerings. So let's suppose we wanted to connect to a storage account that we held in Azure. If we connected to that over the public peering of Azure, we would connect over our ExpressRoute circuit, go inside Microsoft's Edge network, and we'd be truncated from there and be able to access the public endpoint of our storage. Yes, the storage has a public connection, but our access to it would be over a private network channel. Then finally, ExpressRoute also offers the option for a Microsoft peering. That is where our clients on our network are able to connect directly to services like Office 365, Dynamics 365, Skype for Business, Azure Active Directory, and Intune without any of that traffic going out over the public internet. Again, that's done by that traffic being routed out over the ExpressRoute circuit, and the ExpressRoute circuit truncates inside Microsoft's Edge network, i.e. the traffic truncates inside the Azure data center. So what that means is we do get a secure connection to Office 365 or any of those Microsoft software as a service offerings without being exposed to the public internet. One of the things that we found over the past few years is that obviously the ExpressRoute circuit adds a level of cost to the cost of getting data from our on-prem network to Azure. So ExpressRoute circuits tend to be used mostly for virtual network connections into the private peering. A lot of organizations can then trust that the SSL pipes that Office 365 and Azure AD type applications use natively for software level encryption over the public internet provide rigorous enough controls. So it's increasingly popular that even though ExpressRoute provides the capability to use a public and a Microsoft peering, many organizations are choosing not to implement that and to allow that traffic to go over the public internet, unless there's a specific need for the traffic not to flow over the public internet. Azure provides us some built-in tools to check out our connectivity back to our on-premise environment. Both the VPN gateway and the Azure ExpressRoute circuit have these tools built into them. So when we look in the properties of a VPN connection, we can look at things like its properties. We can look at the shared access key as well to see if the credentials we've been issued out to the connecting client are correct. So there's a process that we should follow through when troubleshooting on-prem connectivity. The first one is to check whether our on-premises VPN device has been validated. That means, is it one of the devices that's on Microsoft's approved list of devices? Then we verify that the key we've shared to allow that remote device to authenticate against our network is correct. It's entirely possible that sometimes copying and pasting from one desktop session to another or copying into a web browser session may have caused some minor corruption to the key characters in the key. We should also verify that the VPN's peer IP address is listed in our local network gateway in Azure. If that's not the case, Azure doesn't know where to route traffic back to the on-premises network to. We should check our UDR and NSG settings on our gateway subnet just to make sure that routing and network security groups aren't preventing traffic from flowing over the gateway subnet. We need to check the on-premises VPN device's external interface has been added to the VPN. We should verify that subnets match the subnets in Azure and the subnets on premises match what's listed in the gateway network, the local network gateway exactly. We also should have a look and verify that the Azure Gateway Health Probe is monitoring the connectivity correctly and resolve any issues that the gateway probe is identifying with the connection. We should check whether or not the on-premises VPN appliance has stored the perfect forward security, has the perfect forward security feature enabled. If not, that's going to make it difficult for the VPN connection to implement security properly, and that could result in traffic being dropped. If we've checked through each of these steps and we're still having problems with connectivity, we could try replacing the on-prem device, or we can also log a support request with Microsoft to ask for help with the issue. Let's take a look at the exercises that we're going to come across in Lab 4. In Lab 4, we're going to go through several exercises that give us some hands-on experience on the modules we've just talked about in this course. We're going to create a virtual network, we're going to add a public IP address to a virtual machine, we're going to add an additional virtual network card to a virtual machine, we're going to create both an internal and an external Azure Network Load Balancer, we're going to implement several configurations in Azure Traffic Manager, we're going to create a VNet to VNet peering, and then finally, we're going to create a VNet to VNet VPN. Thanks very much for taking the time to review the course today. Enjoy yourselves with Lab 4, and I look forward to seeing you on the next module.